Hello everyone, I'm Hussain Sajid from Professor Hosuk Choi's laboratory. Actually, I am a master's student from Chungnam National University. So today I would like to present about Black-titania glass fiber and its properties and application in solar to steam. So here are the contents. I will present introduction, optimization, characterization, and application, and as well as conclusion for my material. So here is the introduction. So we have motivation from gold nanoparticles which are currently using for solar to steam, which are relatively very expensive. But we proposed an objective to introduce Black-titania as an prospective alternative material for solar to steam generation application, and develop the synthesis procedure of scalable, durable, and highly efficient light absorber. So my precursor material is titanium nanoxide, which is an anatase particle, and the particle size is 14 to 20 nanometer. And the second one is titanium big particle, and the particle size is 450 nanometer. And the next one is which I used as a precursor. There is the P25 reducer titanium dioxide nanopowder. The particle size for that one is 20 nanometer. Because it's really cheaper, it is cheaper than titanium nanoxide and big particles. So therefore, I can consider the P25 reducer titanium nanoxide as a precursor. So here is the mechanism for my material. Actually, the band gap for the white titanium is 3.2 electron volt. So therefore its color it's white. It has poor absorptions. So I did treatment normally I took this figure from the literature. So actually we introduce oxygen vacancies by annealing, and we narrow the band gap for the Black-titania is 2.75 electron volt, and this is the structural distortion for the Black-titania. As you can see, there are visible oxygen vacancies in the Black-titania. So the next one is synthesis from white titanium to Black-titania. So first, as I earlier mentioned, that I used P25 reducer as a precursor material, and I made a solution 10% solution in ethanol and take it to the vacuum tube furnace. So the annealing condition in the tubular furnace is the temperature is 520 degrees Celsius, and the temperature raise is 5 degrees per minute, and total hold of time is 3 hours, and the gauge pressure is minus 0.01 bar. And then after that one, I made after that one, I made a concentration of 20 milligram per 100 milliliter solution, ethanol, and then I load it by vacuum deposition on the glass fiber filter, and then I cut it into 1.5 into 1.5 centimeters square for my STS experiment. And here is the temperature versus time versus temperature profile graph. So for my sample in vacuum tube furnace. So here is the solar to steam figure. So the solar light comes and incident on the absorber, and absorption happen, and then after that the light energy heat converted to the heat energy, and then the operation starts. Actually, the surface for the STS system must be hydrophilic in order to get higher evaporation rate. So the next one is like optimization. I optimize my sample, and like the problem which I have, that is the more loading volume. When I loaded the volume on the glass fiber filter by vacuum filtration method, so there is like the surface become hydrophobic. Like you can see the spectra like here. So for the 30 ml it's fine, like it is hydrophilic. Like after the 30 ml, like 40, 50 and 60. So the evaporation rate is higher. Sorry, the absorbance is higher, but the hydrophobicity is the problem. So therefore I proposed a solution that is like I use the plasma treatment to introduce the functional group attached to the surface to make it hydrophilic. So the plasma condition for that one is like plasma power is, that is the optimized condition. So it is like the plasma power is 150 watt and gas flow is like 5 liter per minute, and the treatment time is 10 minutes. So here are the photographs for after the plasma treatment. And the next one is the contact angle measurement. So like as I mentioned, as I earlier showed the absorption spectra. So this is like without plasma treatment, the first one like the contact angle is 0. And the second one is like the plasma treated 60 ml loading amount on the glass fiber. So the contact angle is like 0, it is like super hydrophilic. So the next one is like the hydrophobic. So the plasma, the loading amount is 40 ml. So the average contact angle is 5.62 degrees. So the next one is the characterization. I analyze the TGA for my material. The TGA for my material, like you can see, for the glass fiber there is no certain weight loss, but for the Black-titania, weight loss starts from 300 degrees Celsius because of the I use ethyl cellulose as a binder. So the ethyl cellulose decomposition temperature is like 300 degrees Celsius. So the next one is the XRD analysis. The XRD analysis indicates that there is no crystal structure changes upon low temperature aniline. And the next one is the XPS analysis. The XPS analysis indicates that we introduced as I mentioned in the previous slides that we introduced the oxygen vacancies. So here we got oxygen vacancies for the Black-titania. The atomic ratio for the oxygen vacancies is 8.1 atomic ratio as compared to the White-titania. So the next one is the results for SAM and TAM analysis. So for the SAM analysis, the particle size for the White-titania is for the White and Black-titania is 20 to 40 nanometer. So it means that it is truly nanoparticle before and after aniline, and after that the TAM analysis indicates that there are the diameter for the lattice ranges is 0.335 nanometer for the plane 101, which indicates that the particles are most of the particles are anatase particle. So, but there are the creation of amorphous outer layer in the Black-titania. So it means that it is the proof of the Black-titania that it is the proof of Black-titania in which the amorphous layer, like disorder layer, creates after annealing. So the next one is the application of my material in STS. So like the solar to steam experiment setup is like the first one is in the photograph is like polystyrene foam, which is used as an insulator, and the next one is the water channel, and the third photograph is for like it indicates that the DA water in the HDPE bottle, and the next one is the zero sun and under one sun illumination photographs. So the next one is solar to steam performance. So the non-plasma treated spectral like mass change and the evaporation rate, it is like the evaporation rate is 1.32 kilogram per meter square into hours for the loading amount of 50 ml. And the loading amount 4.2 milligram per centimeter square. The operation rate is like 1.37. So the next one is like plasma treated sample. So the mass change and evaporation rate is like different. When the loading amount increases, the evaporation rate and the evaporation rate also increases. So here are the results, like for the plasma 40 ml and 50 ml. So this is the like trend, like different loading amount. When the loading amount increases, like the evaporation rate is 1.34, like 1.37, and I got the final evaporation rate 1.43, which is maximum. So the next one is like the plasma versus non-plasma treatment. So here you can see the difference. Like the evaporation rate is like 1.3 and 1.4. So plasma really helped in the hydrophilicity of my material. The next one is the long-term stability and absorption spectra. So here you can see the results. So the before plasma treatment, the absorptance is like 93%, but after plasma treatment it is like 88% and 91%, and the maximum is like 94%. So the next one is the conclusion. The Black-titania was successfully synthesized and deposited on glass fiber filter by vacuum filtration method, and we developed a cost-effective and stable band absorber. And the Black-titania demonstrated good evaporation rate like the 1.43, 1.37, and 1.34 and 1.35 for the different loading amount like 50, 60, and 40 and 30. The solar absorbance is also like the maximum is like 94.43%. Thank you so much, and I will also thankful to the Professor Hosuk Choi and the BK21 and BRLB who supported us, and I'm also thankful to my colleagues like Dr. Larina, Dr. Alexi, and Mr. and Miss Inhi Park, and Mr. Wanton. Thank you so much.
Okay. The question from the audience.
I have one question.
Okay, please.
Can you tell me why do you choose glass fiber substrate?
Because of the thermal stability. Because of the thermal stability and high surface area, therefore I choose the glass fiber as a substrate.
Okay, any other question from the audience? Okay.
Could I ask you one question?
Yes.
You mentioned that your material is stable with high temperature.
Yes.
So have you ever tried to test the high sun simulation for your material?
I tried high sun illumination, and I am trying. Like I got some results, but that is my future work. I will try that one as well. Thank you.
Okay, thank you.